Alright, so this tutorial is going to be on an interesting phenomenon called single slit diffraction. It's very similar to double slit diffraction, but it has some unexpected consequences, so pay close attention to some of the details. The equation that comes out of this and the profile is nothing radically different, but it has some subtleties to it. So let's take a look at the concept here. Okay, so let's say we have some parallel waves coming in and we have a single slit. We want to know what would a pattern look like on a distance screen. Okay, so the slit size is approximately approximately the same as the wavelength. We might expect to see just basically a uniform pattern here. In other words, we might expect to see something like this. Right, the waves spread out. Okay, and they will hit all parts of the screen. However, that does not happen, and that's perhaps the unexpected part. You will get an interference pattern, even though there's only one slit. Okay, so we want to know what's going on. So if we shine light through a narrow slit, roughly the same order of that, we will get a central bright spot, a definite minimum, then a very weak maximum, and then it will repeat itself, getting smaller and smaller in terms of the maximum. So how can this occur? This is definitely interference, so where's the interference coming from? Alright, so here we have to revisit Huygens Principle. Alright, and according to Huygens Principle, if the slit is wide enough, okay, it's not arbitrarily small, it acts as a new source of wavelets, like any opening does, and these wavelets will spread out and interfere as if we had a multiple slit. So in this diagram here, here's a slit. Now we've zoomed in on it, and I've drawn 3 arbitrary dots within that. Those represent the wavelets. So when the waves propagate out from each wavelet, you can see how they would start to interfere. And even though I haven't done a very good job, you can kind of see how you're going to get bands of constructive and destructive interference. So the question we want to address now is, well, how do we reproduce this intensity profile? How wide is it? In fact, if you look closely, you'll notice that the width of this maximum is much larger than the width of successive ones. So we want to focus our analysis on that aspect for the rest of this lesson. So let's look at this from a slightly different standpoint. Okay, so here's where we want to pay attention to detail. Think of any questions that you might have that come up if you're not following this. So let's say again we have our rays of light coming in. These would represent our parallel waves. Now a few things can happen. We're going to look at 2 scenarios on the same diagram. So the first scenario is pretty easy. Some of the light is going to pass straight through and not bend. Okay, I'm not going to draw those. So we would expect right here a central bright spot. Okay, so all the waves are going to meet here in phase like we saw with double slits, so there's nothing new with that. Now, if we want to develop the intensity pattern, we want to look at when the first minimum occurs. So you can see right here we've drawn such that the first minimum occurs here. Now the question is, what angle does it occur at, and why is it the way it is? So let's break this down a little bit. We have here a situation, the angle chosen right here. So if we measure up from the central bright spot to here, there's our diffraction angle. That is going to be the same as that angle right there. Okay, and we choose an angle such that the distance this ray travels versus the furthest ray is exactly 1 wavelength. So the path difference from the top to the bottom is exactly 1 wavelength. Yet if you're paying attention, you'll see this is a minimum. That's very different than what we saw with double slit, where when there was a 1 wavelength path difference, we had a maximum. So why? Well, between the top ray and the bottom ray, we have some other rays. You can see 3 others shown right here. Halfway between the top and the bottom, the path difference is going to be lambda over 2. So this bottom ray travels a full wavelength greater than the top ray, but the middle ray is going to travel a half a wavelength further. So we can break that down and basically say that if we start in the middle, this ray right here will exactly cancel out that ray, and then the ray above it will cancel out that ray, and a ray above it will cancel out another ray. We haven't drawn, we've just drawn 5 here, but we have arbitrarily large number of these. So every ray that diffracts has a partner that is exactly a half a wavelength away from it, or half a wavelength path difference. So they'll all cancel out to form a minimum here, and we could do it symmetrically on the other side and get a minimum in equal distance down there. So we can see why, if our minima occur right here and right here, why we have such a big bright spot. Okay? So we can come up with a very simple equation for this. It basically says when you have a slit, that the angle that this occurs, okay, is simply going to be equal to lambda over b, where b is the width of the slit. This is very similar to what we had for double slit, except for this is generally for a first order maximum. Technically, there is a sign in front of this, but generally these angles are so small we can put a theta there and it will come out to be in radians. However, if it is a significantly large one, we would have to do an inverse sign to get it in degrees. If the opening is an aperture, circular, like a pinhole, an eye, your pupil in your eye, a lens, then this angle or this equation changes slightly. It simply becomes, we put a 1.22 in front of there. That's based on a geometry. Okay, so we have a very simple equation for when the first maximum occurs. After that, it follows the same pattern, so we don't really need to worry about that too much. You know, we put a 2 in front of there for the second minimum, 2 in front of here, and 3/2 for the next maximum. So let's do a simple little problem. All right, so let's say we have a wavelength of 750 nanometers going through a circular aperture, that's important, of a certain diameter or width, and we want to determine 2 things. The half angle width, essentially theta right there, because remember it's going to be a minimum on each side of the maximum, and then sketch the intensity profile. All right, we want to be able to do that based on numbers, not just some arbitrary or general shape of a single slit. Okay, so the equation is pretty straightforward. We're going to say theta is going to equal 1.22, that's for the circular part, times the wavelength. The wavelength we're going to put in meters, so we're going to do 750 times 10 to the negative 9th meters, that's the nano. And then we got to be careful of the units for the aperture. It's in millimeters, so we're going to convert that to meters. So we're going to call that 5 times 10 to the negative 3 times 10 to the negative 3, which is simply 10 to the negative 6, but I want you to understand where it comes from. All right. You can punch the numbers in your calculator for yourself. I trust you can do this. We get an answer of 0.183 radians. Okay, if you want an angle in degrees, you do an inverse sine of this. This would be about 10 degrees, okay? But we're going to keep our profile in radians. What that means then, our intensity profile, here is 0 radians. We're going to expect a large peak relative to everything else. Let's let this first mark here represent our first minimum. Okay, so we just found our first minimum is 0.183 here. We'll call this negative 0.183 on the other side. And so we're going to drop it down. Okay, and then our next minimum is going to occur here on each mark. So notice that the next minimum is half the length of the full peak, and so it's going to be much smaller though, and then get smaller yet and smaller yet as we keep moving out. Okay, so the key thing to understand about single slit diffraction is you get an interference pattern because of Huygens Principle. What separates it from double slit is you have a very wide, bright central peak, and then the peaks fall off dramatically thereafter. And that the width of the central maximum is twice that of every maximum thereafter, for reasons that we explained earlier. All right, one last problem, very basic. Whoops. Okay, and what two changes would we make physically to make the central maximum smaller? I don't mean shorter, we mean less wide. It's not clear here, okay? All right, well, the width of this depends on two factors. We know that the angle is proportional to lambda, and inversely proportional to the slit width, so distortion here on the screen. Okay, so it makes sense. We would have a shorter wavelength. All right, so if the original wavelength is in the red part of the spectrum, we might want, let's say, blue. Okay, and then we want this to be bigger for this to be smaller, so we need a wider aperture. And we will see the significance of this for the concept of resolution. Wide apertures give you a big advantage in terms of better resolution for reasons we'll see in the next lesson.